All right, today we are getting into a really foundational piece of system design, consistent hashing. It's basically the secret sauce that lets massive, distributed systems scale up without completely falling apart. So let's just jump right into the big question. You've got a growing pile of data, and you need to spread it out across a whole fleet of servers. How do you do it? Well, the most obvious answer, the one that probably comes to mind first, seems simple enough. But it's hiding a catastrophic flaw. And that first pass idea is usually the modulo approach. It makes perfect sense, right? You just take a key for your data, run it through some hash function to get a number, and then you use the modulo operator with n, your total number of servers. Boom, you know exactly which server gets the data. Super simple.
And you know what? As long as your system is totally static and never ever changes, this works beautifully. Just look at this. We've got our 4 servers, and the keys are spread out nice and evenly. Everything is perfectly balanced and predictable. What could possibly go wrong?
Well, in the real world, systems are never static. Servers fail all the time. Or maybe your traffic is growing and you need to add more capacity. And this is the exact moment where our simple, common-sense solution begins to crack and then shatter. And this is where the meltdown happens. It's called the rehashing problem. As soon as one server disappears, our number of servers, n, changes from 4 to 3. And that means the formula, hash%3, gives a completely different answer for almost every single key in the system. It's not just the data on the failed server that has to move. It's practically all the data. This triggers a massive system-wide data shuffle. A storm of failed lookups, it's absolute chaos. So clearly, that approach is a non-starter for any system that needs to be reliable. We need a much smarter, more elegant solution. And that solution is consistent hashing. It's a technique designed specifically to handle servers coming and going, all while minimizing this disastrous data reshuffling. Okay, so let's build this idea from the ground up. Forget the modulo operator for a minute. Instead, I want you to imagine the entire range of possible outputs from our hash function, just as a big long line. Now, take that line, bend it, and connect the two ends. What you have now is a circle, or what we're going to call a hash ring. This is the core concept.
So the first thing we do is put our actual servers onto this abstract ring. We take the name or IP address of each server, run it through that same hash function, and that determines its position on the circle. Just like that, our servers now have a specific address in this continuous hash space.
Now for the really clever part. How do we figure out where a piece of data lives? It's simple. We hash the data's key to find its own spot on the ring, and then we just walk clockwise around the circle until we hit the very first server we see, and that server is the owner. The crucial insight here is that this rule has nothing to do with the total number of servers. Okay, the theory sounds great, but this is system design, so we have to ask, how does it hold up under pressure? This is the real test. Let's see if this design actually delivers on those key non-functional requirements we care about, like availability and resilience. Okay, check this out. We're going to add a new server, S4, onto the ring. It gets hashed and lands in its spot. Now, what happens to the keys? Well, the only keys that are affected are the ones that were previously going to S0, but are now before S4. So in this case, only key 0 has to move. Everything else stays exactly where it is. The disruption is tiny and totally localized. I mean, this comparison says it all, doesn't it? On the left, with the old modulo method, losing a server triggers a system-wide firestorm. On the right, with consistent hashing, when server S1 goes away, only its keys are calmly handed off to the next server in line, S2. We've literally gone from total system failure to a predictable, manageable, localized update. It's a huge difference. Okay, this is a massive improvement for sure, but in great engineering, we're always looking for the edge cases. And even this really elegant ring design has a couple of subtle problems we still need to iron out. It's not quite perfect yet. So here are the 2 potential traps. First, if a server goes down, its neighbor now inherits all of its keys. That could suddenly double the load on that one poor server. And second, just by pure random luck, when you hash your servers, they could end up all clumped together on one side of the ring, leading to a really imbalanced load from the very beginning. So how do we fix this? With another really clever abstraction called virtual nodes. The idea is, instead of putting each server on the ring just once,
What if we gave each physical machine multiple identities and scattered them all over the ring?
And you can see exactly how this smooths things out. Server 0 isn't just one point anymore. It's here, here, and here. Same for server 1. By breaking up a single server's responsibility into many smaller chunks all around the ring, you make it statistically way more likely that the data, and therefore the load, is spread evenly across your actual machines. And this, of course, leads us to a classic engineering trade-off. The more virtual nodes you create, the better your load balancing will be. It becomes much more fine-grained. The downside? Well, now you have to keep track of all this metadata, mapping all these virtual points back to physical servers. So you get to tune this number, balancing that perfect load distribution against memory overhead. Okay, let's step back for a second and bring this all together. Why have we gone through all this trouble? Why is consistent hashing such a fundamental pattern that every system designer needs to understand? Well, it's because it directly solves for some of the most critical non-functional requirements of any distributed system. It gives you true scalability because adding and removing servers is cheap and doesn't cause chaos. It improves availability because one node failing doesn't take everything down with it. And it creates resilience because the whole system can just gracefully adapt to constant change. And that really leaves us with a final thought here. This core idea of taking a linear problem and mapping it onto a ring is an incredibly powerful mental model. You see it pop up in distributed databases, in peer-to-peer networks, in CDNs. It just makes you wonder, right? What other big, messy engineering problems out there could be simplified if we just started thinking in a circle?